Let us again consider second example to write the KVL expression. So as we already discussed, so we are assuming positive sign for voltage drop. So let us start writing the KVL equation for first loop. So if we are starting from this point, so there is a voltage rise. So we shall consider for all voltage rise it is negative sign, for all voltage drop it is positive sign. So we shall start from here. It is minus V in because there is a voltage rise, and plus V1 because it is a voltage drop, then plus V2 there is again a voltage drop, and plus V3 there is a voltage drop. So this can be rewritten as V in is equal to V1 plus V2 plus V3. So here I listed what are this voltages. V1, which is nothing but current flowing through the resistor R1 and its resistance. So V1 is I1 into R1. Similarly, I have written the values of other voltage drops. So similarly we can write it for second loop, that is this loop. So while writing the equation for the second loop, we are again starting from this point. So here there is a voltage rise. So voltage rise, this is, we have named it as V3. It is minus V3. Then there is a voltage drop plus V4. There is again one more voltage drop plus V5. So this can be rewritten as V3 is equal to V4 plus V5. So we'll consider how can we. So this expression for first equation was V in is equal to V1 plus V2 plus V3, where we are writing what is the expression for V1, V2, V3 in terms of the current and the resistance. So that can be rewritten in the form of V in is equal to, now I am grouping the resistances which have current only I1 and resistance which has got only current I2. So this is for the first loop. The second loop equation on the similar lines looks like this. So this is V3, where V3 is nothing but I1 minus I2 into I3. So this is written what is V4, what is V5. This can be further rewritten by grouping currents of same values on one side and other values on the right hand side. So I1 into R3 is equal to, here you can see all are I2s, so it is taken as a common factor. We have I1 is equal to so and so. Now let us consider the third example. That is a slightly different circuit. Here we have three loops. So this is loop 1, loop 2, loop 3. Now naming of the loop is left to the individual. So here you can name it as this is 1, 2, 3, or this is 1, that is 2, this is 3. So let us start trying to identify what is the voltage drop. Here I have written the final equation. So I want each one of you to try to get this final equation. Let us try to find out what is the voltage V1 to V5. So as we can see, V1 for this assumed current of I1 flowing through loop 1 can be written as I1 into R1. This is I1 into R1. So what is V2? V2 we named this as the voltage drop across R2. This is plus, this is minus. The net current that is flowing here is, this is I1, this is minus I2. I2 is actually going in the opposite direction. So I can write the current flowing through R2 as I1 minus I2 multiplied by R2. So V3 is this. So this is named as V3 because there is a resistor R3. So if you can see here, this V3, this is plus minus. The current direction assumed is in from plus to minus. So I will write V3 as I3 into R3. Similarly, what is V4? V4 can be written as, V4 is from here to here. Here the net current that is flowing here is, this is I2 in this direction, whereas I3 is in the opposite direction. So I have to write this is I2 minus I3 multiplied by R4. Coming to V5, only one current is flowing, that is I2 into R5. So here I have written the final equation. So I have written this as VA so and so. So to get these equations, we have to start with this basic equation, that is VA, this is VA is equal to V1 plus V2. So VA is equal to V1 plus V2. So we are writing what is the expression for V1, which is I1 into R1. The expression for V2 is I1 minus I2 into R2. Upon grouping the currents, upon grouping the coefficients of current, we'll end up with this final equation. Similarly for V2 and V4. Now the last equation is V4 is equal to V3 because this voltage is coming exactly in parallel with, so this V4 is exactly coming in parallel with this, so that's why we end up with this equation. So which is evident here also. This is of course we have grouped it here. So upon writing this V3 and V4, it comes out as this expression. So I want each one of you to get these final equations starting from writing the loop equation. You can see here in the above circuit we have assumed, in example 3, we have assumed the direction of current as clockwise here, clockwise here, clockwise here. So let us consider this is an assumption. So with this as the current direction, we wrote this equation. It is not necessary that you need to assume the current direction in a single clockwise or anti-clockwise. Now here what we are trying to do is we are intentionally assuming for one loop it is in clockwise direction, for third loop also it is in clockwise direction, whereas for the second loop we have assumed it in anti-clockwise direction. So by assuming this as anti-clockwise direction, we are trying to write what is the expression for this. So as we can see here, so what is this V1? Now we are writing what is the expression for the first loop. The applied voltage is drop across this and this. So this is the drop, which is V1. Here the drop is V2. It is very interesting to note what is V2 is. The V2 expression for this particular circuit, because of the assumption, so V2 happens to be, okay, let us start writing what is V1, V2, V3. So V1 happens to be I1 multiplied by R1, whereas V2 is the net current flowing through R2. Of course we named this as V2, which is plus minus, so it is now the current flowing through R2 is, it is actually I1 plus I2. See the difference from the previous case to this case. In the previous case the current flowing through this was I1 minus I2. The I2 was going in the opposite direction, whereas when it comes to the assumption in a different way, now the current flowing through R2 is, this is I1, in the same direction we have I2 also, so that's why it is I1 plus I2 into R2 into R2. So how about V3? V3 we named it as this drop, this is V3, so it is exactly same as in the earlier case, it is I3 into R3. So coming to V4, you can see here both the currents are going in the same direction, that is I3 here, this is I2. So V4 happens to be now, so it is I3 plus I2 into R4. How about V5? V5 is now plus minus, so from here to here it is plus minus, which happens to be I2 into R5. So this is the drop. Just have a look at this loop. So this is the second loop equation. So there is a voltage, rise here. So voltage rise happens to be, so this is the voltage, So we are actually considering this type of moment. So here there is a plus to minus voltage drop, that is V4. I'm starting from here. This is V4. This is again plus to minus. This is again plus to minus. So all are voltage drops. All are voltage drop. That's why it is plus plus plus. So this way, whatever the circuit, whatever the assumption of current flowing, so we are supposed to write for the given circuit, for the given assumption of the current direction, we have to write the. So if you actually start solving the equation as we did for the previous case by assuming the current directions in the same clockwise direction, so this is slightly difficult in terms of solving the getting the solution for the current I1, I2, I3. That's why it is always suggested to assume either clockwise or anti-clockwise direction for all currents. So don't try to assume one in clockwise direction, other in anti-clockwise direction, so that of course we'll get the answers, but it will be bit complicated while solving the solution for your I1, I2 and I3. So it is always recommended to go for the current directions in a single direction, whether it is clockwise all loops or anti-clockwise all loops. So we shall move on to the next example, that is example number 4, which is pretty simple, which is straightforward also. VA is equal to, same current is flowing through both of them, so it is I into R1 plus I into R2. So of course we can name it as V1 plus V2. So this is V1, this is V2. So that's why VA is equal to this into this plus this. I'm taking common I. So what is VB? VB is the voltage across the resistor R2. So whenever only VB is written, it is always with respect to ground the voltage. So I am writing what is VB is equal to. VB is equal to, so here we are writing the expression of I in the form of V by R. So we know that I is equal to V by R. In this case, V is VA, the R is R1 plus R2. So in the previous examples, we actually wrote the expression for VB as VA into R2 by R1 plus R2. So this is how you are getting the expression for VB. That is, the voltage across R2 is nothing but RVA into R2 by R1 plus R2. So let us move on to the next question. Just have a look at this circuit diagram. So with the concept that what you learned so far, I want you to verify this equation number 1 and 2 and write the correct equation if there are any corrections required for the above equation. If the equation is wrong, you correct it. So that's what is the task for you people. Carefully observe the circuit diagram and the equation. Try to identify the mistake in the equation, if at all, if any mistakes are there. Okay, we shall move on to the next circuit. We shall have a look at. Now we shall move on to a circuit bit complicated in nature. If you have a DC voltage source, a diode and a resistor, now how do we start analyzing the circuit diagram? If you are asked to find what is, if you are asked to write what is the loop equation for this diode, we are supposed to replace it by its equivalent circuit when it is forward biased. So why we are replacing this by a voltage source of V gamma is because we know that when the diode is forward biased, it will have a potential barrier created, so which is represented by a voltage V gamma, which is the cut-in voltage, which is hardly 0.6 to 0.7 volts. Now again, now it is, you have this circuit having a diode is now replaced by a circuit which you know that okay, if you have a resistors and voltage sources, you know how to write a KVL for this. So now this complicated circuit diagram with diode has become a very simple circuit diagram by replacing the diode by its equivalent voltage source. So we end up with an expression for this as, so here we are assuming a current of ID flowing through both the diode and the resistor because they are in series. So VA is equal to V gamma plus ID into R. ID into R. So let us move on to uh, the circuits which will be repeatedly seeing in the most of the electronic circuit, especially in the labs also. Now you can see we have a transistor, a BJT, being represented by a symbol which you already know by this. So this is a symbol of a transistor where we have the indication of this is base, this is collector, this is emitter. So that's what is written here, the base terminal, the collector terminal, and the emitter terminal. So since there is a base and emitter, we always have a potential difference being represented by VBE. So this VBE is nothing but the DC voltage between the base and the emitter. B is at a higher potential and E is at a lower potential. So suppose if you start writing the KVL for the first loop. So as we can see here, this is the first equation which is written for the base loop. So since this is connected to base, we call it as a base loop. So we have this VBB is equal to this drop because the current flowing through this is IB, so it's IB into RB plus VB. So this is plus to minus a voltage drop. So this is again a drop of IB into RB is there. So that's why this is plus. This is also plus because this is taken onto the left hand side. This is also plus, otherwise this would have been minus on the right hand side. Similarly, we can write the KVL for the collector loop also. So I can see this is applied voltage VCC is equal to the drop across this. The drop across this resistor is, this is plus minus, so which is nothing but IC into RC. So this is the current flowing through this. So resistance is RC. So VCC is equal to IC into RC plus VC. So see here, there is a voltage between collector and emitter. This is plus, this is minus. That's why this is named as VCE. So in most of the cases, we are interested in what is the voltage VCE. So that's why this can be rewritten as VC is equal to VCC minus IC into RC. So this is a very typical, very important equation which will be repeatedly using to find out whether the transistor is in active region, cutoff region, or linear region. We shall move on to one more circuit. Now the difference between this circuit and this circuit, there is a resistor RE at the emitter, whereas there is no resistor at the emitter point. So emitter was directly grounded. Now it is not directly grounded. It is, the emitter is grounded through a resistor RE. Now you carefully try to understand some relations here. So there is a emitter current IE which is equal to IC plus IB, that is emitter current is equal to collector current plus base current. So we are writing a KVL for this. So be careful here. So in the previous cases, so we have assumed the current direction in the loop as, suppose if you consider this particular equation, this particular circuit diagram. So this was current I1. So we thought, okay, this is a current I1 flowing in the loop, whereas there is a current flowing in this opposite direction. The effective current flowing through this was I1 minus I2. So this is, we are assuming there is a current I1, there is a current I2 in the loops. So similarly, we know that the current flowing through the base is IB, the current flowing through the emitter is IE. So we are exclusively writing what is the current that is flowing in this arm. It is not the loop current, it is the current that is flowing in this arm. So it becomes very easy to write the KVL, the applied voltage, or you can rewrite it as, so since there is a voltage rise, you can write it as minus VBB plus there is a voltage drop. This is plus and minus, so voltage drop is IB into RB, and there is one more voltage drop, there is plus minus here, it is plus V suffix B, so this is VB, so there is one more voltage drop, that is VE, which is nothing but IE into RE. So this is IE into RE, which is named as VE here. So upon rewriting this equation, this minus will go on to the left hand side and will become plus. So this is how we can able to write the expression for the base loop by considering the current through this arm as base, this arm as the emitter current. On the same lines, we can write the expression for the KVL expression for the second loop, which happens to be VCC, the applied voltage, is equal to this drop plus the drop across collector and emitter, and this. Usually while writing the equation, students tend to forget this VCE because they don't find a resistor. Even though there is no resistor externally visible, but effectively this will offer some resistance, so we're going to represent it by VCE. So that's what is this. VCC is equal to this drop, that is IC into RC, plus VCE and IE into RE. So this is what is the expression for the second one. Of course, we can find what is the current IC, so which is nothing but VRC, that is voltage across resistor RC by the resistance RC. We can find what is current IE, and we can find what is current IB. So it's purely the voltage across the resistor divided by the resistance. Now just have a look at this. Now this is a circuit which we usually come across. So this will be written as a plus VDD, and this is ground, this is VGG, so on so. So when this is only plus VGG, so we have to think that okay, there is a plus of that battery is there, the negative is connected to ground. So this exactly looks like this. It is effectively written as this one. So once this is there, so we can easily write the KVL. For this loop, for the drain loop, of course we have drain, gate, source for the MOSFETs. So we can write this minus VDD. So we can start writing this as minus VDD plus the current flowing through the resistor RD is ID, that is ID into RD, plus VDS equal to 0, because summation of the current in a loop is equal to 0. So voltage rise, there is a voltage drop, we named it as plus minus because the current direction is like this, and this is again we assumed it as plus minus, so VDS. And this VGG is nothing but VGS because there is no resistor connected here. Similarly, as we did it for a BJT, so VC is important, VC in the form of VCC minus ICRC minus IARE. Here also we are interested in knowing what is VDS. So VDS for a given MOSFET is equal to VD minus IDRD in this particular circuit diagram.